Welcome. In this video we begin Unit 4 on linear functions and models. I'll take 2 days for this unit, and on this first day we look at 4.1, properties of linear functions and linear models. In fact, we will cover all 4 objectives today in section 4.1. So let's get started. Graphing linear functions. We've talked about lines and we've talked about functions, so now is a good time to start talking about linear functions. What is a linear function? A linear function is a function of the form f of x equals mx plus b. So you can imagine this is a lot like the line y equals mx plus b. They are very similar. We're just kind of thinking about this line now as a function. For example, f of x equals 30x plus 100, that is a linear function, or g of x equals negative 2x plus 500, that is a linear function. How would I graph a given linear function? Let's say I need to graph h of x equals negative 2x plus 3. Well, I can maybe plot a few points. What is h of 0? If I plug in 0 for x, then all I end up with is 3. What is h of 1? I plug in 1 for x, so h of 1 is negative 2 plus 3. That's 1. And one more. How about h of 2? So h of 2, well, let's see here. Negative 2 times, I put in a 2 for x and 3. So that's negative 4 plus 3, which is negative 1. So let's plot these points out. H of 0 equals 3, so I plug in 0, 3. H of 1 equals 1, I will plot 1, 1. H of 2 equals negative 1, so 2, negative 1. And it looks like these 3 points lie on a line. And I could continue this in both directions and graph out a nice line that goes through those points. Notice this line has y-intercept 3. And the line has slope negative 2. So really, there's this connection. To graph the function f of x equals mx plus b, graph the line with slope m and y-intercept b. The graph of the function really is just the line, and that's what makes it a linear function. Average rate of change. So if f of x equals mx plus b, then m is the constant average rate of change of the function f. When we talk about a line, we talk about m as being the slope of the line. But when we talk about a function, we think of m as being the rate of change of the function. It's really the same idea with just 2 different words on it. Do you remember, when we talked about the average rate of change of a function, we picked 2 points on a function and we asked what was the slope between those 2 points. Well, let's do the same thing with a line. Suppose that my function f is the linear function f of x equals mx plus b, and I graph that thing out and it's some line. I'll pick 2 points on the line, x1, y1, x2, y2. What is the average rate of change between those 2 points? And do you remember, this was the formula that I used to figure it out. F of x2 minus f of x1 divided by x2 minus x1. And let's just quickly go through this and see what that boils down to. F of x2 is mx2 plus b. F of x1 is mx1 plus b. I'll distribute the negative sign, so that negative sign comes out there. Oh, look what happens. Now I have a plus b and a minus b, so I can just write this m times x2 minus m times x1 all over x2 minus x1. And now I can factor out the m. So I get m times the quantity x2 minus x1 over x2 minus x1. But now I have a common factor of x2 minus x1, and all I'm left with is the m. So this confirms something we probably guessed already, that m is the average rate of change of this function. Also, the idea is that it is a constant rate of change, that no matter where I put these 2 points on the line, I will get the same value of m. The rate of change of this function doesn't vary for different values of the points that I pick. What if a function is given to us that is not drawn out as a line? If the function is graphed as a line, I already know it's a linear function. But here are two functions given as tables. How can I tell if it's actually a linear function or not? And here's where we look at the rate of change. Look at the function on the left. My x values vary 1, 2, 3, 4, 5. But how do the y values, how do the function values vary? 50 to 55, they go up by 5. 55 to 60, up by 5. 60 to 65, it increases by 5. 65 to 70 increases by 5. Look at this. This rate of change of the function is 5. It is constantly 5 at all points. So this is a linear function. But how about the function on the right? Again, x goes 1, 2, 3, 4, 5. What do my function values do? They increase by 10. Then from 60 to 72, so that's an increase of 12. Already, I can tell right now, this is not a linear function. This is a non-linear function. Just to complete this out, it looks like maybe the next increase is an increase of 14, and then 4. Yeah, so clearly this is not a linear function. One more example. What about this function? Let me pause for a second. Do you think, is this linear or not linear? So if I look at the change in my function values, it's 2, and then 4, and then 8, and then 2 again. So our first guess is that it is not linear. But in fact, it actually is linear, because did you notice there's something else? My x values were not given consistently. The x values increased by 1, and then 2, and then 4, and then 1 again. To figure out rate of change, I really need the change in the function divided by change in x. So change in the function divided by change in x, which is, change in function is a lot like the change in y. It's like the change in y over change in x. And so I really need to think 2 divided by 1. So 2 divided by 1, that's 2. 4 divided by 2. 4 divided by 2 equals 2. 8 divided by 4. 8 divided by 4 equals 2. 2 divided by 1. 2 divided by 1 equals 2. And now I can see that I really do have a constant rate of change. It is 2 every time. If I were to graph this thing out, if I were to graph all those points, 130, 232, 436, 844, 946, those points do lie on a line. Now, the points aren't equally spaced, but that's okay. The points lie on a line, and so this is a linear function. How can I tell if a linear function is increasing, decreasing, or constant? Well, look at the slope. In this first case, my slope is 1/2, which is a positive number, and a positive number tells me the function is increasing. In the second situation, my slope is -2. -2 is a negative number, and the function is decreasing. In the third situation, well, I don't really have a coefficient on x, or you could think that the coefficient on x is 0. It's like I have a 0 slope, and so my y does not change at all, and this is a constant function. So positive slope means that the function is increasing, negative slope means that the function is decreasing, and 0 slope means that my function is constant. Let's turn our attention away from linear functions and think about this idea of linear models. Sometimes a real-life situation can be described with a linear function. We say that the function is a model for the situation. Here's an example. A cab ride costs $5 to start, and then $2 for every mile. So the moment you sit into that cab, even if you haven't traveled anywhere, it costs you $5. And then for your first mile, that costs $2. So you have to pay the initial 5 plus the 2, so $7. Drawing out a quick chart might look something like this. Traveling 0 miles will cost me $5, but then after 1 mile, the total cost is 7. After 2 miles, the cost is 9. After 3 miles, the cost is 11, and so on. The initial cost is $5. The rate of change is $2 for every mile. And look, now I have the information I need to make my linear function. I have an initial value and a rate of change. That's like the b in y equals mx plus b, and this is the m for my slope. So my cost function, c of x, is 2x plus 5. And see how that matches up with the table. It's a nice linear function, and it reflects the values in the table. All right, here's an example. A little more involved and a little more interesting. When you own a car, its value decreases over time. Suppose you bought a car for $31,500, and every year its value decreases by $4,500. Four things I want you to think about. A, write a linear function v of x for the value of the car after x years. B, graph the function, just make a little sketch. C, what is the value of the car after 3 years? And D, when will the value of the car be $9,000? So really pause the video at this point and see what you can do with this problem. Give it your best shot and then start it up again when you are ready to check your work. All right, go to it. Let's see how you did. So A, write a linear function. V of x is negative 4,500x plus $31,500. Here's the graph. At 0, put x value of 0 in there, it starts off at the point 31,500 high, and then it decreases over time. So for every increase in x, the function value will drop 4,500. C, what is the value of the car after 3 years? Well, in this case, all I need to do is plug in 3 for x, v of 3, and we end up with 18,000. The trickiest part is probably D. When will the value of the car be $9,000? So in this case, I need to solve the equation v of x equals 9,000. So I need to figure out what is the x that makes the value 9,000. So replace v of x with its actual expression, negative 4,500x plus 31,500 equals 9,000. I can subtract 31,500 from both sides, and then divide both sides by negative 4,500, and it ends up with the answer being 5. So what that means is that after 5 years, the value of the car will be $9,000. Here's another example. For a certain cricket species, the rate at which it chirps is a linear function of the temperature. At 52 degrees Fahrenheit, it chirps at 20 chirps per minute. Then, for each degree rise in temperature, the cricket's chirping rate increases by 4 chirps per minute. This is kind of curious, and again, this actually is a real-life situation. So, as the temperature gets warmer, these crickets start chirping faster and faster and faster. Find the chirping speed, c, as a function of temperature, t. And once again, pause the video, give this your best shot, and then start it up again when you are ready to check your work. All right, let's take a look. So I find it useful to write out the first few values. So when the temperature is 52, the speed is 20. When the temperature is 53, the speed is 24. 54, the speed is 28, and so on. So for every degree increase in temperature, the speed of the chirping increases by 4. I know that the general form for this function is c of t equals mt plus b. I'm just using the variable t instead of the variable x, but that's okay. And my m in this situation will be 4. That's the rate of change. So I'm at the point where I know that c of t equals 4t plus b, but here's the real tricky part in this problem. What is the b? Like, what is this initial chirping speed? I don't relish the thought, but I could work this table backwards until I get to 0, and then I would figure out what that chirping speed is, that initial chirping speed. But there must be a better way of doing it. And yes, there is. How about this? We know that the chirping speed at a temperature of 52 is 20. So how can I use that? Oh, just plug that 52 into my function. 4 times 52 plus b is 20. And now I can figure out what that missing b is. 4 times 52 is 208. Subtract 208 from both sides. b equals -188, and that gives us a formula for tripping speed. C of t equals 4t minus 188. Alright, and that concludes the material for 4.1 and gives us a good start to this unit on linear functions and linear models.